simply 2 new degrees of freedom put in. So once you put these things in, you demand the so-called gauge invariance similar to the gauge invariance that exists in QED. And that is gauge invariance if you do not only the global transformation here, but if you make this a local transformation, and this gauge field will help you to maintain the gauge invariance for this whole theory. This whole theory is a local gauge invariance with space-time dependent function in these formulas. Now let's find a vacuum. Assume this vacuum expectation value of this one is not zero, so that this vacuum breaks the symmetry. There's a non-zero vacuum expectation value. So this is the non-zero vacuum expectation value. Say that's V, vacuum expectation value. Therefore, the electroweak symmetry is broken because of this non-zero scale. It's not symmetric anymore. Then if you continue to rewrite the theory, you find to expand the real world around the vacuum. That's what we always do in quantum mechanics. You do perturbation around the vacuum. When you do that, you'll find this imaginary field here has mixing with A field. This is not canonically normalized, so it's no good. We have to make this a diagonal. When we make this diagonal, it's simply this form. This is nothing but a gauge transformation. You can move this degree of freedom away by gauge transformation, because if you change the gauge, physics remains the same. So you simply do this gauge transformation, it's called a unitary gauge. If you simply change the gauge like this, and you basically diagonalize this field here, and the result Lagrangian becomes such a nice simple form. The simple form is a real component that exists. The real component here has mass here. Okay, this is the vector field here becomes massive by absorbing this the additional degree of freedom and also keeping this vacuum expectation value. This is a leftover new particle. This leftover you have to search for. That is a Higgs from his demonstration. No more the complex field. The imaginary part is gone. Doesn't appear in your Lagrangian anymore. And that is exactly the so-called magic of the Higgs mechanism. So because of this, this is a particular choice with unitary gauge, but this one disappeared in the spectrum. The massless Boson, which is thought to be a showstopper for the theory, actually does not really appear in your particle spectrum. Okay? So this massive photon swallows this additional degree of freedom, becomes massive. So Pauli's criticism actually was fixed by this. So if you count the degree of freedom here, this is before the electroweak symmetry breaking here. If I have 2 scalars, one real, one imaginary, 2 massive degree of freedom for the photon. The photon has 2 degrees of freedom, as we know, polarizations. But now it turns out, under this electroweak symmetry breaking, there's only 1 scalar degree of freedom left, that is Higgs. And 3 degrees of freedom, the exact match for the massive gauge field. Now you see these 2 different problems help each other to cure each other. So this is really amazing magic. So massless gauge boson plus additional masses, either one is problem enough, but they help each other to make this the real world even more like the reality. So massive gauge boson plus no Boson boson anymore. So this is truly remarkable mechanism. So this is so-called Higgs mechanism. Okay. Now we want to observe a few deep insights here. Okay. One thing that why the Higgs discovery was non-trivial. From this description, it seems to be very trivial, but in fact, the Higgs mechanism does not mean the existence of Higgs particle, because WZ has 3 degrees of freedom. So from theoretical viewpoint, you only need 3 Boson bosons to absorb into this, but you don't need the Higgs doublets to the complex doublet for 4 degrees of freedom. As long as you have 3, just like a pions, this is a little bit messy expression. If you parameterize this into 3 field only, not the Higgs field like a 4 complex degree of freedom, you still can generate a W and Z masses. That's sufficient to generate W and Z masses. No additional scalar there in the real world. You don't need a Higgs to just simply give the masses. However, that theory is not going to be valid much arbitrarily high energies. So it's only about 2 TeV, so this theory will break. The unitarity will be valid. This was the major argument for the LIC and for the SIC at that time as well, because at this level, we know something is going to happen. The theory will have to replace. Either we find something like Higgs to help us, we don't find Higgs, we find something else. to help you to understand the theory. That was a major argument for that time. So the fact that the existence of a light weakly coupled Higgs boson, as we discovered, tells you something. Tells you this kind of simple proposition is not right, and you should have this the Higgs magnetism exactly like the Higgs construction. So it tells you that maybe it gave us some hint for physics beyond standard model for the construction. Maybe it tells you the UV completion is important information. Maybe the renormalizability is important criterion we want to keep when we construct theory. So the existence of this Higgs tells you something beyond the simple formalism already. So Higgs did not have to exist, but it does exist, tells you something we should learn. Secondly,
but you will need the double to give mass to the quarks, right? So
no, you can write exactly non-linear realization to give quarks. You could respect the symmetry. Yeah.
Without the four degrees.
Exactly, non-linear realization. Yes, yes. Famous papers by LeCosPA and company. This non-linear realization. You use the same non-linear realization to do this. It's mathematically easy to see that you use your doublets, you send Higgs mass to infinity, and you exactly same result. You send Higgs mass to infinity. Yeah.
No, I understand.
Yeah. You can, but it's not unitary theory. So the value unitarity. It's not renormalizable theory.
Yeah. Sigma 1. Yeah.
Non-linear sigma 1. Exactly non-linear sigma 1. Okay. Now another lesson. Now we said we had four forces. This is a new one. The lambda is a new interaction. It's really self-interaction. More self-interaction than the gluons. Gluons have different colors. This one has the exact same quantum number. Self-interaction. New interaction. New force. Weakly coupled. From standard model, this parameter is free, but from the measurements, now, from the Higgs mass measurement, now, we know this parameter is 1/8, very close to 1/8. It's the 0.10. This is a new coupling constant, dimensionless, new coupling constant. You could say this is a new force, self-interaction, because of this discovery. Well, it is a new fundamental force like all the other forces, gate forces, we think. Or maybe this is just like a van der Waals force that comes from a resultant Coulomb interactions, and you have a more fundamental interaction to give you this. That's exactly what we want to find out. Okay? So we don't know whether this is fundamental force. In other theories beyond standard model, such as supersymmetry, this constant is not free. This constant, new force, is predicted in connection, due to symmetry, in connection with the gauge theory. That's much nicer, right? Now we understand this interaction, new force, is not a new fundamental force. It is related to other interactions by this additional symmetry. That will be really interesting. Even in other theories, such as strong dynamics, composite theory, the strong dynamics, you also could calculate this quantity and give you this prediction. It's not new force, but a new parameter that can be expressed by more fundamental parameters. So that's exactly what we want to find out in the future. But the composite here has similar problems. In supersymmetry, this prediction is a little bit too small. We need to have additional thin and dense to make this constant more similar to this one. But for strong dynamics, it's something similar because the root suppression is common. But even now, nevertheless, this observation here tells you it may be related to more fundamental interactions, but it gives us some kind of deep trouble or challenge for new physics already. Already at this point, the measurements may teach us something for the possible construction of theories beyond standard model already. So it's very, very interesting already. But let's look at the high energies. I mentioned to you that because of the anti-screening effects, the coupling constant changes. The coupling constant changes with the distance. It's nature. The coupling constant always changes with distance. How this coupling constant of this coupling constant change? It is not asymptotic free, similar to the QE case. If you run this one to ultra high energy, it may blow up. But either you have a very low starting point, or otherwise it blows up very quickly. So it turned out, the good news for us, the 125 GeV, 206 GeV Higgs mass set this to be 1/8. It is small enough. We do not hit into this shaded region would give you this so-called Landau pole the theory. Our Higgs mass tells you the coupling constant is small enough, even if not asymptotic free, we do not hit the problem even up to Planck scale. That's good news. So the good news tells us a very, very important lesson. It tells us that if the standard model is, and it is, this coupling constant Higgs mass may be perturbatively applicable for this theory to a very, very high energy, even maybe valid all the way up to Planck scale and so on. But also give us good news. As Eva also mentioned, give us the applicable room to have new physics such as gravitification, such as maybe heavy neutrino mass to help us for the seesaw mechanism. You have a big room to expect some possible new physics to come in for this the lab standard model case. Okay. On the other hand, as we mentioned, Eva also mentioned that because of rather a small cupping constant here, because of rather large top quark mass, and this the overall vacuum stability may be somewhere maybe a quasi-stable, matter-stable vacuum rather than absolutely stable vacuum. But it's probably not immediately a problem, but it's kind of curious for us to see whether this indicates anything. So nevertheless, the standard model with the new cupping constant here, it is a very important quantity. This is our target for the next generation of experiments to do Higgs physics to great detail to understand the nature of these new interactions. Finally, the connection with the superconductivity. The electroweak symmetry breaking does generate exactly the same behavior. Let's think about the normal superconductivity. In our normal electromagnetic interactions, photons are massless. It propagates infinitely far away with the propagation speed of light, as we know. So this is the we call this a dispersion relation. This is a relation between the energy and the momentum, and there's no speed. Speed here is speed is a c. It's no additional mass term. Okay? This is normal force. Therefore, it's a long range. So here is the medium. In this medium, when it's in the normal phase, electromagnetic field propagates as it is with the speed of light. Of course, it speed light up to the index of the refraction. However, under the superconducting phase, under this particular phase, you lower the temperature lower and lower, and then you hit the critical temperature. Then this material becomes superconducting. If this material becomes superconducting, we know this Meissner effect. The electromagnetic field doesn't come in anymore, which tells you the electromagnetic field does come in, but short range. The short range is given by this exponential suppression. It's called the London penetration length. So it doesn't mean it doesn't come in at all. It only tells you the electromagnetic field propagated under the superconducting phase with short range interaction. It doesn't propagate infinitely further away. So this is the interpretation for our short range force and long range force, given whether there is a mass term in your dispersion relation or not. This is similar for electric interaction. So typically, the photon will generate a mass here, 1 over lambda. So this typically is kind of a Kelvins. That's what the low temperature superconductivity is. We know that it's a few kelvins for the temperature. And I give you this photon mass in more or less in this range. BCS is correct theory. We understand that this pretty well for the low temperature superconductivity. But this is similar for the electroweak superconductivity because the gauge boson mass is set to 100 GeV. 100 GeV translates into something like 10 to the 15 Kelvin temperature. We are leaving nothing but a superconducting phase for the electroweak interaction. That means that at the early universe, everything is symmetric, all the particles are massless, including the weak bosons, all massless. But when the temperature cools down up to this cold value, 10 to the 15th Kelvin, up to that cold value, suddenly there's phase transition. During this phase transition, that's electroweak symmetry breaking. After the phase transition, we're leaving there. That's why the weak force is a short range. It's not that these particles are intrinsically different from photons. Same. That standard model tells you they're same. But the reason the short range is we are living in the superconducting phase for the weak interaction. Nothing more than that. Okay? So it's very simple. The physics are all related. Okay? We can understand one from the other. Okay? So that's another lesson. The Higgs potential is of a Landau-Ginzburg form, very similar to the superconducting description, but it is different. Landau-Ginzburg theory is just a poor parameterization. It's even not a correct theory. We know the correct theory is BCS. Okay? It's dynamic. But our Higgs presentation here so far, the interaction here, the Higgs particle itself is a fundamental interaction, as far as we know so far. That's why we want to test the Higgs is fundamental, or the interaction is fundamental or not. Okay? So far, the interaction tells you it is fundamentally different from the Landau-Ginzburg parameterization. Parameterization is the same, but physics is much profound in that case. Okay, now we're set. We have the standard model, beautiful standard model. It works, may well be up to the Planck scale. Someone said most of the underlying principles have been formally established. Now, standard model, experiments, everything. Eminent physicists, they did not name what I was, remarked that the future truth of the physical science are to be looked for the 6 decimal digits, just precision measurements, nothing more than that. That's what Yifan was asking, whether it is. Who said this? Remember who said this? When this was said? Last year? Last month? When was this? After his discovery? After Michelson, 1894. That was the time he said. Michelson himself, Michelson-Morley experiment. Okay, that experiment he did not realize the immediate importance. That was really the moving off point for that mature physics into the modern physics. The 50s, we know. Now we see, maybe history will repeat itself. We think we have a perfect theory to describe everything we know so far. How could we know this is it? Maybe history will repeat itself. People keep saying this over and over again. But let's see what happens. So our director, Nima, so we set up this, with the Yifan strong support, we set up this center. It's called the Center for Future High-Energy Physics in Manhattan. And Nima was the driving force to mediate a lot of activities. Put it into his center. He said the central questions today are not details anymore because we have this such a beautiful theory. However, we may have some fundamental breakthrough. The origin of space-time, the connection between the ultra-high energy, ultraviolet, and the infrared energy, and maybe the standard model becomes the only effective field theory. The more fundamental theory will come out of that to tell us how to understand the standard model in this setting. Okay, so let's see what we can do. Of course, Higgs is new. Higgs is the only thing we have new, and we want to have this Higgs to be studied to great detail as much as we can. I call this a Higgs lamppost. It's pretty dark around, but we have to try hard to see what we can find. So that's the future. Now see the Higgs discovery paper has generated a huge impact. I think there was even just a few months ago, I approached 36 countries citation already. It covers from broad topics for the Higgs discovery. Integration of the standard model, exploration for new physics beyond standard model, okay. Application to in astronomy and cosmology, cosmology concepts, and string physics, all possible related, and even some philosophical aspects. You never know how the broad impact the discovery would be. Okay. So I will leave out the philosophical aspect. Let's get into a few possible examples. This is the Higgs model I mentioned to you. This was very similar to the form that Peter Higgs first proposed. But by that time, he only used 2 components. Now here, of course, the 2 components, but you complex field with the 4 components here. So this is only generalization into the non-abelian theory. So this is a Higgs set. In this form, everything is predicted. Standard model parameters are all measured. Sorry, the parameters are not explained, but all the parameters are measured. All of them. So because of the beta decay, because of Higgs mass, Higgs particle discovery, I mentioned to you the Higgs mass parameter here is measured, and the new coupling constant, lambda, is measured, 1.8. Okay. We seem to know everything. It's just like this, the vacuum expectation value is around here, and the vacuum transition tells us this, the electric phase transition from the symmetrical phase to the broken phase. It's weakly coupled, but because it's weakly coupled, and because of rather a small mass, it is a very smooth second order phase transition. It is not very interesting. It basically tells you that everything is washed out. It's no new physics from the cosmological effect will be transmitted to us, which I'm talking about the so-called electric baryogenesis. So if this is the case, well, the cosmology is completely washed out during this time in the early universe. We don't have a more direct path. Is really the case? In fact, we don't know. Yifan showed you this part already. This is all we know. We know the position at the V. We know the slope, the Higgs mass. We only know this very little, only for the 2 terms in your Taylor expansion. Okay, do the Taylor expansion, but only know 2 terms. How can you think we know everything? Okay. Here could be anything. It's so-called Coleman-Weinberg potential. You can generate new physics from different scales to come down to the electric scale. You can generate the higher dimensional operators. You could even generate non-analytical forms as well. So if you do believe the new physics is a different kind of new physics. So therefore, you can modify this coupling constant, the term, into different forms, even negative sign, with new physics. Okay. If that is the case, the order of one transition, order of one correction to the triple Higgs coupling could be very possible. In certain theory, you can modify this as a 7/3, sometimes a 5/3 of these corrections. It's order one correction. If you can change this by order one correction, you can generate the phase transition dramatically different. You could have a first order phase transition. We don't know how the phase transition happened during the electroweak phase transition. We only knew that we are living in the superconducting phase. There was a phase transition at the 10 to the 15 Kelvin from the mass. We did not know the nature of that. We did not know the connection with the cosmology or so on and so forth, because we even did not measure this quantity to a higher accuracy. So far, the lambda is determined only from standard model assumption. There's no direct measurement here. The direct measurement will come from the very crude for LHC, okay, 50% or so. I will come on that, and the future the Higgs factory, which is maybe 30%, and the SPPC, which is less than 10%, which is the quality reducing. Okay, that was the first thing. Second thing about this naturalness, if I also comment on that. Ken Wilson, of course, the grandfather of this normalization concepts and the understanding the field theory better than anybody else, he said, oh, thanks God, we don't have a scalar, because scalar is so bad. Scalar particles are the only kind, free particles, whose mass term does not break any symmetry and or gate symmetry, so the mass can be anything. We just don't know whether there's a such thing. But unfortunately, we found one. We found one we even did not know mass. The mass fraction, as Yifang said, the mass fraction is relatively like 1% times the scale. If you think your theory is valid all the way up to Planck scale, lambda is 10 to the 19, then this fraction is the fine-tuned in 10 to the 33 digits. Yifang showed you the numbers. Okay. You need to have the fine-tune 33 first digits to cancel out, give you 1. However, if the new physics comes in around TeV scale, that fine-tune is not too bad in that regard. Okay. So you either have an order from TeV scale new physics to come in to give you this the quadratic fraction cancellation, or you get into some possible relation between ultraviolet and infrared, which people usually have no idea yet. We don't know string theory well enough to give us yet, or you have to give up. If you gave up, you call it multiverse and anthropic. I don't think that's my question I want to pursue, because it's not quite scientific to me. Okay? So I would not argue about that. And this is a theoretical exploration. People still don't know, but this is natural thing for us to pursue. Let me I have to show my daughter here. So she was playing with this the Coke can, and suddenly she was shouting at me, "Hey, Dad!" And I came back. Oh, there will be a few seconds. I took the picture and stopped. You will think why she was asking me for that. You'll be surprised too, because that's unbelievable. This unbelievableness is calculated to be 10 to minus 3 fine-tune. It's essentially the small area here divided by the possible normal stable area, but it's a fine-tune. It's only 10 to minus 3. 10 to minus 3 fine-tune here means that you try 1,000 times, you may have the good luck to make this happen once for a few seconds. You wouldn't believe that. If you walk in to see this happening, you do not dare to continue to walk. You want to see, wow, what is happening? Maybe someone is doing something for that. Or what? You would not believe this is natural. You should not believe this. The unnaturalness is a severe question. To me, it's very strong motivation to think about other reasons, solutions for the Higgs mass. Why Higgs mass is so different from everything else. Okay. The third thing about dark matter. The dark matter is very pressing. We know that dark matter most likely particle origin. Okay. If a dark matter is particle origin, the best hope is that Higgs is new. Higgs is someone we don't know very well. Higgs can do anything. In particular, Wilson told us this operator has no protection. This operator has no protection. That is the origin why the Higgs mass has no protection. If there's no protection, this operator can do anything. This operator can interact with dark sector. That's what we call this very likely the dark matter may have something to do with the Higgs sector. We call this a Higgs particle. The new sector may interact with this through this operator. New fermions, new scalars, or whatever. So okay, so now you can even make the connection between the direct search, this is the cross-section current bonds, future lux determinant, future 110 determinant to search for this. The green regions are, here you can see, this is the Z mass to give you the correct radical density. Here the Higgs mass to give you the correct radical density. Here are the supersymmetry theory with the new Higgs bosons. So you can see that the new Higgs particles and in the standard model and in the SUSY sector may have the direct prediction to see how interaction should be and to merge into the comparison with the direct search. Direct documented detection may have a lot to do with our indirect search, collateral search as well. So this is very important for us to pursue as well. So here are the Higgs regions, and here is very predictable when we have the theory. Finally, so if someone tells you we have these parameters all measured, and you think we are done with the standard model, now I want to show you that it's so strange. Electroweak scale is 250 GeV, and Higgs mass, WZ, and top quark mass are all more or less in the natural range, which is 100 GeV. But quark mass is lighter and lighter, and the fermion mass is lighter and lighter. Electron mass only half MeV. Okay. So this scale is 15 orders of magnitude up to the Planck scale, and you believe there's nothing in between? The standard model is valid all up to the Planck scale? And then you're not mentioning that the neutrino mass is so much smaller, and so far we don't know the absolute values, we only know the mass difference. Mass difference is pretty small. The electron volt 10 to the minus 2, electron volt 10 to the minus 3. In that region, it's another order, 15 order of magnitude to the electroweak scale, to the value. Everything in the standard model is proportional to the single parameter value. This single parameter gives you the mass difference with a 30 order of magnitude. Well, it's very strange. Why with the quarks and quarks have such a pattern? Why the neutrino mixing is in such a form? We have no clue. We have parameters measured from the experiment. We also need the new CP violation sources to give the bioasymmetry. All of these may be related to the Higgs-Yukawa interaction. So the Higgs may serve as a pivot into this flavor sector. I have no time to discuss the flavor sector. The flavor sector is extremely pressing, extremely important issue for us to pursue, but we just don't know the scale. The only problem is that we don't know the scale. We don't know where the scale is. The scale may be higher, maybe above our access. Unlike the Higgs mass region that we more or less know is electricity. But we know something is going to happen. So some people are even quote me saying that we know the flavor of physics must exist somewhere, but the only thing we don't know the scale. We have to keep pushing. Okay. So finally, just give you the impression that it can be related to the neutrino mass, because everything is proportional to the Higgs vacuum expectation value. The smallness of this may be due to a new physics above this. We call it seesaw magnetism. This is seesaw magnetism. High scale give you the less scale, but the pivotal point is the Higgs phase transition vacuum expectation value. We call type 1 seesaw to have a new heavy red hat neutrinos. Okay. We call type 2 seesaw to have a new Higgs sector without assuming the heavy neutrinos. We have type 3 seesaw to have a new triplet leptons. Either one of them would be able to generate the Majorana neutrino mass to realize this called seesaw magnetism by introducing new scale, but also by making use of the Higgs value. Okay. So therefore, you see that there's a very rich possibilities that will generate neutrino mass to understand neutrino mass at a fundamental level beyond this standard. Okay. And also, as we know that from the CCMS search, they are searching for this flavor physics, and there is even some kind of a very weak indication for the channel. But watch out, the Higgs sector with the flavor sector with the Higgs physics may be very interesting. Now we come to the future detection. So how much time I have? Time is up. Okay, let's stop. No, I'm just joking. So this part is similar to what Yifan described anyway. So I'll probably give you a few flavor and jump into the conclusions here. So in the future is brilliant. Future is bright. Okay. So we are marching into the phase 2 of the LSC, and the run 2 is going to resume maybe end of March or beginning of April, asking our experimental colleagues here. And it's going to take us to the 2030, so hopefully we'll have the luminosity upgrade. And if everything works out okay, we will try to support the Japanese effort to have a linear collider